Hello, my name is Ambar. Today I'll be talking to you about the project I did in collaboration with Levon and Brian. It's like Daniel said, predicting cross-section images of particle beam for humor using neural networks. First of all, what is the humor? Well, the humor is a particle accelerator at the University of Maryland. It is actually an electronic ring. So you know, particle accelerators can be used in a wide range of areas from medicine to energy production. The electronic ring at Maryland it's only used for research purpose. It generates a stream of electrons from a gun with low energy and relative high. What this means is that this in the beam, making its movement functions really particularly since it's nonlinear. The motivation for this project is that due to limited space, diagnostic tools cannot be placed at all locations on an accelerator, limiting the diagnostic information available. Virtual diagnostic can be implemented to fill in missing information. So imagine this is your particle accelerator and that the things here are your cameras. Then if you run this and you take an image here and you take an image here, uh, you don't know what's happening in all this space. So if the image here comes with an error you were not expecting, you wouldn't know how exactly uh, to adjust things here. You would just be changing parameters randomly to see if you get what you really want. Machine learning techniques can be used to train with existing diagnostic data and predict how the beam will be looking at every location, so you can know exactly where the error occurred. So we use neural networks because they are known for their well performance in time series predictions. And as you may know, they are an application of machine learning, which in turn is a branch of artificial intelligence. On a general spectrum, this will be the shape of a neural network. So you have different layers. Each layer contains nodes. These nodes can have functions. In this case, the bias is just a number. And so you take an input, you apply the function it has, you multiply that result with a weight, you feed that result to another node. Each node does this to different layers, and then at the end you compare your result with what you were expecting the data to be. And let's say you were expecting a 5 and you get a 7, then you have to reshape either the weight or the connections between these nodes so that the result is lower in value. You do this a lot of times so that your network can actually learn the function you're trying to predict. The process of this project, first of all, we use a simplified model of the humor. We didn't use experimental data. This simplified model is pictured here. So you can imagine each of these objects to be magnets or tools to reshape the beam. And the advantage of using a simulation is that you can get information at every time step around the beam, around the ring. You can have, so that way you can verify that what your neural network is predicting is accurate to what it really is. Here is the training process. So when you give information to your neural network and it is training, you'll get a graph like this. The y-axis represents the mean absolute error of your predictions. So what you want is to reduce this number to a lower possible value. The difference between the orange and the blue graph is not really that important. What you really want to know is that you need the orange line to be above the blue one. If not, you're probably overfitting your network. The first step of our project was to predict just the X position of the data. So this means our neural network will predict only one feature, which is known to be possible for really easy task for our neural network. Here you have the black graph will be the simulation, the input data we were trying to predict, and the blue one would be the prediction given by our neural network. As you can see, it is really accurate. It predicted the overall behavior, and even in these cases where the where it was a little bit out of phase, it was moved, the overall behavior was the same. So we can say it predicted correctly this input. So we move on to predicting actual images. This will be how the images from the humor look. They are taken with phosphorus screens. And because these images are really high resolution, so imagine each pixel to be a feature for our neural network to predict, then we will have, if we feed in this real image, we will have thousands of features, and that's not really possible for a computer to do in a short amount of time. So what we did was creating just a 15 by 15 pixel image, which is a little bit more uh, quick for the computer to predict. These were our results. So we did two types of predictions. The first one was static. We gave the model 3 images as input, and then the model gave us 3 images as output, prediction, 3 images into the future. And as you can see, when we keep it like that, the overall movement of the beam was reasonably close to what the real beam looked like. So what was out of, but the shape was not exactly how we wanted it to be. Here you can see it's a little bit more circular, it's more centered, and here it's more rectangular, and sometimes it just covers the whole picture. But overall, the movement is not that far. On the other hand, we also did fitting predictions, which means we gave the neural network 3 images as input. Then the neural network gave us 3 images as prediction. We took those 3 images and fed it back to the neural network as input, and it predicted the next 3 images in time. As you can see, the result was really not good in any aspect. The overall movement of the beam is just up and down. It's not anywhere close to what the real model is doing. And the shape is also off. It is not centered. It's just a lot of points around the image. Future work for this project. Well, the next step will be to upgrade the image resolution, and maybe even if we want to make more accurate predictions while maintaining the accuracy, even incrementing it. After the resolution and accuracy is reasonable enough, project can then take experimental data from the humor as opposed to simulation data. We can train the model and make real virtual diagnostic predictions at locations without any information. Thank you all for your time, and thanks my mentors and Daniel. Is there any questions?